when we want to map one surface to another, there's an inconsistency between parallel lines. Parallel lines in one patch are curved in the other patch, and it is true about the inverse of the map. We want to make this inconsistency in parallelism to go away. Suppose we move an arrow on the surface of a sphere. To make the arrow tangent to the surface, move the arrow a little bit and then project it onto the surface. All tangent vectors make a right angle with the radius of the sphere. Now, if the sphere is the skin of the globe, then moving an arrow tangent to the spherical Earth is like traveling along a path. Furthermore, if we insist on keeping the orientation of our arrow constant with respect to its initial orientation, then we may find an inconsistency traveling around a loop. In order to make sense of the change in orientation, we need to study the path. What is it that makes some paths preserve the orientation of the tangent arrow? Of all the possible paths on the globe, how can we generate the one that keeps the initial orientation of a tangent vector constant? First, let E and M be smooth manifolds. Then pi from E into M is a surjective and differentiable map between smooth manifolds, meaning every element in M has some corresponding element in E via the map pi. Now, let x in M be a point. A fiber of pi over point x is called E sub x and defined as a non-empty subset of E as follows. E sub x equals pi inverse of x equals pi inverse of the singleton of x, subset of E. The singleton of x is taken to be the manifold E by the inverse of the map pi. However, to have a set of more than one point, let U be a subset of M, U subset of M. Then we have E sub U equals pi inverse of U, subset of E. In this case, E sub U is the part of E above the subset U. Next, define a global section of the map pi like this: S from M into E. Considering the definition of pi from E into M, the definition of the global section implies that the composition of pi and S is the identity map. Pi OS equals the identity over M. A section such as S can be a local one if we take a subset of M in the domain U subset of M. Then a local section is defined as S from U into E. In a similar way, the definition of the local section implies that its composition with pi is the identity map over the subset. Pi OS equals the identity over U. For all points x in subset U, the section S of x is in the fiber E sub x of pi above x, if and only if S is a local section of pi. In this pointwise case, the map pi is restricted to subset U. In other words, pi from E into U, where U is a subset of M. In general, for 2 points x not equal to y in M that are not equal, the fibers E sub x and E sub y of pi over x and y may not be embedded submanifolds of E, or even be diffeomorphic. That means there may not be a differentiable and invertible map that takes fiber E sub x into fiber E sub y from the tangent spaces of E sub x and E sub y over points x and y may not be naturally linear subspaces of the tangent space of E, but it is different in the special instance where manifold E equals M cross F is the product of M and the general fiber F, and pi as a map is the projection onto the first factor, pi from M cross F into M. If that is the case, then fibers E sub x and E sub y in F of pi over the two distinct points x not equal to y in M are embedded submanifolds of E and diffeomorphic. To explain it more clearly, given that condition, there exists an invertible and smooth map taking one fiber to the other, and the tangent spaces of the fibers are directly summed with their respective dual subspaces at points in the fibers to span the whole tangent space of the manifold E at points of pi over x and y. Therefore, fiber bundles are the generalization of products E equals M cross F as twisted products. Before we define the Hopf action, first describe a scalar multiplication rule between vectors and numbers. Let R denote real numbers, C complex numbers, and H quaternionic numbers. Now, define the linear right action by scalar multiplication for K equals R, C, and H as the following. K n plus 1 set minus the singleton of 0 times K star to K n plus 1 set minus the singleton of 0. The linear right action by multiplication is called a free action because for x in Kn plus 1 set minus the singleton of 0 and y in K star, the multiplication x times y yields x if and only if y equals the identity as the identity element. For example, if we let x equals the vector 0, 1, 0 and y equals 1, then the result of the scalar multiplication is the vector 0, 1, 0 times 1 equals 0, 1, 0. In addition, we define the unit n-sphere, for the Hopf action works on spheres. So, the unit sphere of dimension n is defined as S super n is defined as the set W sub 1, W sub 2 through W sub n plus 1 in Rn plus 1 such that the summation of the W sub I squared equals 1. Now, Hopf actions are defined as free actions. Sn times S0 to Sn, S2n plus 1 times S1 to S2n plus 1, S4n plus 3 times S3 to S4n plus 3, given by x comma lambda maps to x lambda. An example of a Hopf action is the multiplication of the 3 sphere S3 isomorphic to SU2 subset of C2 on the right by the unit circle S1 isomorphic to U1 subset of C. Define the Hopf action as the map capital Phi from S3 times S1 into S3. What's more, the Hopf action has two properties. Number 1, V comma W times lambda times mu equals V comma W times lambda first and then times mu. Number 2, V comma W times 1 equals V comma W for all V and W in S3 and lambda and mu in S1. The next idea is about the orbit of a point in the three-sphere S3 under the Hopf action. The orbit map is defined as phi from S1 into S3 given by lambda maps to V0, W0 times lambda for all V0 and W0 in S3. The orbit map phi is injective and free, meaning that a point in S3 cannot have many points in S1. Furthermore, the Hopf action capital phi from S1 into the diffeomorphisms of S3 is a homomorphism. It preserves S3. The Hopf action being a free action implies that the orbit of every point V0 and W0 in S3 is an embedded circle S1. Back to the topic of fiber bundles. We recall that the part of manifold E over subset U equals E sub U equals pi inverse of U subset of E, where U is a subset of M. Here, there is an equivalence relation in the fiber E sub x of pi over x, since the orbit of a point in fiber E sub x by phi collapses onto a single point x in U via the projection map pi from S3 into S3 quotient tilde. After the collapse of every fiber in manifold E, the quotient space S3 quotient S1 is seen to be the projective complex line CP1 isomorphic to S2. The projective complex line is the ratio of two complex numbers. To see how the space of S3 is connected compared to S1, note that every closed loop in S3 is shrinkable to a single point in a continuous way, tracing a local section. However, a closed loop in S1 is not shrinkable to a single point. This fact makes S3 a simply connected space and S1 a not simply connected space. We are now almost equipped with the tools to define a fiber bundle in a formal way. Let E, F, and M be manifolds. The projection map pi from E into M is a surjective and differentiable map. Every element in M has some element in E. Then E, pi, M, and F is called a fiber bundle, or a locally trivial fibration, or a locally trivial bundle. If, for every x in M, there exists an open neighborhood U subset of M around the point x, such that the map pi restricted to E sub U can be trivialized as a cross product. Remember that E sub U is the part of E of pi over U. In other words, E, pi, M, and F is called a fiber bundle if there exists a diffeomorphism phi sub U from E sub U into U cross F, such that PR1 O phi sub U equals pi, meaning the projection onto the first factor of the trivialization map phi sub U is the same as the map pi. Also, a fiber bundle is denoted by F to E to M via pi. In this notation, E denotes the total space, M the base manifold, F the general fiber, pi the projection, and U, phi sub U a local trivialization or bundle chart. using a local trivialization u comma phi sub u defined as e sub x equals pi inverse of x, we find that the fiber E sub x is an embedded submanifold of the total space E for every point x in M, meaning the tangent space of fiber E sub x is a linear subspace of the tangent space of E. The composition of the local trivialization with the projection onto the second factor gives us yet another useful map between fibers E sub x over x and the general fiber F. It is a differentiable and invertible map, a diffeomorphism, and equals phi sub u equals PR2 O phi sub u evaluated at E sub x from E sub x into F, given that the local trivialization phi sub u from E sub u into u cross F is a diffeomorphism, invertible and smooth. The projection PR1 from u cross 1 into u onto the first factor of phi sub u is a submersion. That is to say, the differential of PR1 is surjective. The differential of PR1 from the tangent space of u cross F into the tangent space of u takes vectors from the tangent space of u cross F into vectors in the tangent space of u, such that every element of Tu has some element in Tu cross F. As a result, the map pi from E into M is also a submersion, which means the differential of pi from the tangent space of E into the tangent space of M is surjective. Every tangent vector in the domain, the tangent space of M, has some tangent vector in the codomain, the tangent space of E. So far, we have established that the bundle projection map, taking points from the total space into points in the base space, pi from E into M, is a submersion. For that reason, the tangent space of the base manifold M is a linear subset of the tangent space of the total space manifold E. Now, we can use the regular value theorem for shining a light on the submersion of pi. Let a point x in M be a regular value of the smooth map pi from E into M, and let the fiber E sub x equals pi inverse of x be the pre-image of the point x. Then, the map pi inverse is an embedded submanifold of E of dimension dim E sub x equals dim E minus dim M, meaning the tangent space of fiber E sub x is a linear subspace of the tangent space of E. We can verify the result of the theorem for the Hopf bundle, F to E to M via pi, where dim E equals 3 and dim M is equal to 2. The regular value theorem implies that the Hopf fiber is one-dimensional. The dimension of E sub x equals 3 minus 2, which is equal to 1, as an embedded submanifold of the total space E. The surface on which the tangent arrow travels may not be flat, but if we zoom in and consider small distances, then the task of preserving tangent vectors becomes easier. Yet, we need to connect these tangent spaces back together to travel globally. But if we map the height as a scalar field over the sphere, then we can cover the whole Earth with charts and adapted frames. A tangent vector is represented by a frame that is adapted to the surface. Then, the frame is a set of orthogonal basis vectors. That makes the vector dual to an orthogonal complement plane. Tracing both objects means that the geometry is free of coordinates. In general, we measure how much the tangent vector tips towards any of the basis vectors of the adapted frame, but we can also make the comparison with a vector field rather than a moving frame. What we get is how much to spin to keep a path parallel. We just have to define an inner product that checks the orthogonality, length, and angle. Model simulations of the long-term dispersal of CS-137 released into the Pacific Ocean of Fukushima. Because of the twin nuclei problem of the cell and the atom, we need to find a way to engineer space-time for interplanetary travel. Read a few sections of The Road to Reality that are related to fiber bundles. Connection 1 forms, scalar products and covectors, and parallel transport are the key ideas for making sense of the choice of trivialization and fiber bundles. Observation of the phase shift of a neutron due to precession in a magnetic field. We have directly observed the sign reversal of the wave function of a fermion produced by its precession of 2 pi radians in a magnetic field using a neutron interferometer. Observation of 2 pi rotations by Frenzel diffraction of neutrons. We report on the first observation of Frenzel diffraction of a beam of unpolarized slow neutrons by individual ferromagnetic domain boundaries. The observed occurrence of a destructive interference in the experiment demonstrates that the phase of a spinor wave function changes by a factor of -1 when the particle described by that wave function is rotated by an odd multiple of 2 pi radians. Geometrize the quantum. This project is inspired by Eric Weinstein's Graph Wall Tone project. Watch visual models on the YouTube channel. For client-side code, read the tests. And for examples on how to build, please check out the models directory. See planethopf.gel for example.